Thanks for the warning, Paul. The next talk's by Niko Naumann. We'll continue talking about p-divisible groups and lots of interesting things.
Yeah, so okay, welcome back. Thank you very much. So here's the definition of a p-divisible group. Over a connective E-infinity ring R, and for prime P, a p-divisible group is a functor G, say from connective R algebras to connective Sept modules with three properties. Firstly, all the values are supposed to be p torsion. So if you invert p, that's 0. Secondly, there is the representability condition. If you take division points of this p-divisible group, then these resulting functors are representable. So this means for every finite abelian p group, you can extract functorially an A, so you map A to the maps of Sept modules from this finite abelian P group M into the value of your p-divisible group. So think M is Sept mod P or something, so then this is exactly the points annihilated by P. And this functor is supposed to be representable, is co-represented by a finite flat R algebra. Finally, the condition of p-divisibility is that it is p-divisible. So the map given by multiplication by p is locally surjective with respect to the finite flat topology. Is locally surjective with respect to the finite flat topology. Yeah, the choice of topology here is a bit technical and irrelevant since all the division points are represented by finite flat schemes. In fact, this will also be surjective with respect to finite topologies. Anyway, okay, that's the formal definition of a p-divisible group. There is our notation is the category of p-divisible group over R is denoted Bt of R, that is for a Bassotti-Tate. This is just synonymous for p-divisible groups. And the only remark maybe I want to make on this definition is for discrete R, we're now in the course of extending these basic notions of formal groups, p-divisible groups, and so forth from classical rings to connective ring spectra. So it's one thing you can always choose here is R just a classical commutative ring, and for discrete R, for this choice, this is equivalent to Tate's notion. It's not exactly the same because Tate, of course, didn't speak about connective Sept modules or stuff like that, but since all these things, the division points are represented by flat algebras. Once R is discrete, all these representing things are also discrete, and so restricting to the test objects here to discrete algebras doesn't lose any information, and it's in that sense that the notion is equivalent to Tate's one. This is kind of important, so we're really this is a proper generalization of the classical notion of a p-divisible group over a discrete ring.
Can I just check I'm still on the right page? So finite is as a module over A, so compact object
over R.
over R. And flat is this thing where it's extended from pi 0.
Yeah, that's the definition of flatness.
And what does surjective mean in 3? Locally, I
You mean the surjective log? Yeah, yeah. Let me just write it out. I mean, so here's a star. So star means IE. Locally, for anywhere you can evaluate your p-divisible group, any connective R algebra, and any value in there, any x and pi naught of g of A, there is some faithfully flat and finite map. So some cover in the named topology such that after extending to this cover, the point becomes divisible by p.
That's on pi 0. Okay.
Yeah. So let me finish this. There is this extension along with some element over b such that p times y is x. Well, we add it. It's f upper star of x in pi naught g of b. So that is what locally p-divisible in that topology means. Anything else? Oh. Okay. So the example is one we've seen before. 2 to 11. We discussed this p-divisible group mu p infinity, but only in a very indirect way in the introduction by saying it's the unique deformation of something we know anyway. But of course, you can also just write down what its functor of points really is. It is the fiber from GM to GM with P inverted. So in that statement, so that's a functor, and the statement is this is a p-divisible group over there you take R equal to the sphere spectrum. So that's a p-divisible group over the sphere spectrum. And now I'd like to spend some time in order to exactly explain this, some theorem 2.208. That is the passage from p-divisible groups to formal groups, which is technically very important. And we've seen the connection in a sense. We're deforming p-divisible groups, but to get an interesting homotopy type in the end, we want to say something about the identity component. So I now try to explain how this identity component works. Assume P is a prime. R is a connective E infinity ring, which is P complete. G over R is a p-divisible group. And here is something technical which we need to contemplate inside the category of connected R algebras. So these are all test objects. This is where the functors are defined, the p-divisible groups, as well as the formal groups. And inside of this, we look at the full subcategory spanned by truncated and p-nilpotent things. Truncated p-nilpotent objects. So maybe you can think R is equal to the p-adic integers, then the discrete objects here are exactly the finite rings of p torsion, so Z mod p to the n, and maybe finite products of these things. And then you thicken up also in the derived direction by allowing finite Postnikov systems of these things with pi naught such a thing, and then you make extensions by p-nilpotent abelian groups. So this is the test category. This is some subcategory on which you can test these things. And then the exact statement is there's a unique formal group G0 over R. So that is supposed to be the identity component of the p-divisible group G. And the statement is there is a unique formal group which on this test category E has the following values. G0 of A is the fiber of G of A mapping canonically to G of A reduced. Okay, by uniqueness it's also functorial and whatnot all, that's clear, but I say 2 words on why that should be true. But before this I make one remark that for discrete R, this is due to messing. And the general proof is an adaptation of Messing's methods, so it's similar. So I want to say 2 things about the proof, I think. On the proof. This is more like a guide to the actual proof, so you know where what happens what. So formal groups are determined on E the precise statement is this was theorem 211. So meaning formal groups are functors on connective algebras. You can restrict those functors to the smaller category of test objects E, and this is a fully faithful functor on formal groups. And this is at least plausible from what I've said, because if you remember, formal groups are co-represented by a spiff of something like power series rings. Then really these functors are the co-limits over the finite truncation of these things, which are truncated polynomial rings, and these live in the test category E. So it's fairly plausible that restricting a formal group to this test category E doesn't lose any information. It's a bit more subtle to characterize the essential image, that is to understand when a functor on E is the restriction of a formal group, and this is what you need in order to address the second point. I mean, of course, this proves the uniqueness. There is at most one formal group which does that, and to get the existence, you need this characterization, which I will not explain, but then you can just write down what this functor is. So this is a very brief synopsis of section 223. So this restricted on these test objects E, the fiber which we want to sell as the value of our formal group, so the fiber of G mapping to G reduced, this is the union over all Frobenius kernels on this p-divisible group. And this is exactly as in Messing's approach, G. So what you're doing here is you look at some nilpotent algebra, you evaluate your p-divisible group, and you look only at those elements which, if you reduce down to the reduced ring, go to 1. So that is some abelian group, and it is annihilated by sufficiently many applications of the Frobenius. Just as in the classical case, in Messing's case, except of course the test objects which you have to play with are a little more complicated now. It's not just discrete rings, but you also have to address the finitely many Postnikov stages an object in E might have. Otherwise the proof is the same.
So what's the Frobenius in this one?
Oh, I won't address this question. Yeah, that was the answer. And yeah. Okay. And then, like classically, it's easy to see that these things are co-represented by truncated polynomial algebras. So as n varies, these assemble into one of those power series rings, and hence are represented by a formal group. That was this brief sketch, too brief as we've seen, but I can always drop this come to Oberwolfach thing. for more. So next is deformations of p-divisible groups. So I'll just write down what the deformation space is. So in this definition 314, if R0 is a commutative ring, this always means discrete commutative ring, ordinary commutative ring. G naught over R0 is a p-divisible group. And we want to discuss deformations of this over complete adic E-infinity rings. So this is, the notation for this is commutative algebras which are complete in their adic topology. Okay. So the space of deformations of the given p-divisible group G0 to the given complete adic ring by definition is the following, and it looks probably a little more cumbersome than you would expect on first thought, and so let me just write it down and then comment on it afterwards. That is the direct limit over all finitely generated ideals of definition of pi naught and for any such you take the following fiber product, take the Bersotti-Tate group over the adic ring itself, you take a map of rings from R0 to pi naught a modulo I. So that is, so to speak, the one of the possible residue rings of the adic ring you're looking at. Like you could have A to be the p-adic sphere, the p-complete sphere, and then this could be anything like Z modulo p to the n, for example. And you take this fiber product over the only thing which is possible, Bersotti-Tate groups over pi naught a over I. So, well, let me at least say in words what a point in this space actually is. So you fix any one finitely generated ideal of definition, and then you have a ring map phi from R0 to pi naught a modulo I. You have a p-divisible group which you want to say is a deformation, but so far there is no relation. So with the reference p-divisible group, and then this fiber product giving a point means you give an isomorphism of p-divisible groups of your reference thing base change to this with the thing you want to identify as a deformation reduced down from A to this small quotient ring pi naught a modulo I. That's what it looks like. So at the very least I hope it now looks like a deformation space, why you would even think of a point in this space as a deformation of G0. Otherwise it looks, as I said, a bit more complicated than you would probably have expected, and the reason is just the proof of the next result. So I will make a very brief remark here. By 343, this is the so-called Derived space of the classifying map of this p-divisible group. So from spec R0 to this moduli stack of p-divisible groups. And this is the general setup of the spectral Schlesinger theory and deformation theory. So to know where the motivation for this Derived space comes from and how it works and so forth, the reference is the root file 18.2.1. So it's a bit reverse engineered. You do not say, oh, this is the deformations I'm interested in, but somewhere in the background there is this huge theory, and you just say, okay, what do you represent for me? And the answer is, look at this map from the Derived space, and if things go well, I will prove that this is represented by a formal spectrum. And then you actually have to work to see that this Derived space has some resemblance with deformations as you want to. There are rather subtle finiteness issues here somewhere, because this moduli stack of p-divisible group is not locally of finite presentation. So you cannot just put Artin's representability theorem on it and everything's fine. It's a bit more subtle, but of course that's all I can say about the next result. Theorem 3.1.15. If p is a prime and R naught, so these are the assumptions in our very first theorem last hour. R naught is F finite, Noetherian FP algebra, G naught over R naught is a non-stationary p-divisible group. Then, of course, the theorem has to be that this deformation functor is representable. So, deformation functor is representable on the category of complete adic rings. By something which then is called R and G naught. This symbol was introduced before, and now it says exactly so. This is representing deformations of spectral p-divisible groups. There is some addition to this, and this E infinity ring is connective and Noetherian. Wow. Yeah, there is really nothing I can say about the proof here, except that this is a fantastic proof of concept to see all these various pieces of input fall into one place. In the end, the theorem is even so fantastic that once you have the general machinery, it tells you the correct assumptions. Because the what you want to do is you want to thicken up this classifying map, and what you do, of course, is you take iterated square zero extension dictated by the cotangent complex. And even for this construction, not in the first step to fall out of the world of connective ring spectra, you have to assume that the cotangent complex of this classifying map is one connective. Otherwise, already the basic idea of proof of making iterated square zero extension wouldn't work. It would immediately introduce negative homotopy groups and lose any control. And it turns out that this assumption, under the additional assumption of Noetherianness, is actually equivalent to R naught being F finite and G naught being non-stationary. So you really, you get the correct assumptions just out of the general machinery.
What does Noetherian mean?
Noetherian for a connective E infinity ring means pi naught is a Noetherian ring in the classical sense, and all the homotopy groups are finitely generated over pi naught. Okay, so that's all I can offer about the existence of this deformation ring. And I'd like to go a little more chaotic now and talk about the Lurie case. Of course, that's a very remarkable achievement here, that there is an independent proof of something with a huge overlap with the Gers-Hopkins-Miller theorem, that Lurie theory admits unique E infinity structure. And I'd like to say, at least try to sketch some of the ideas which go into this. So the setups, recall, specialized as follows. R naught, I will denote this by kappa, is a perfect field of characteristic P. then we start with deforming a one-dimensional connected p-divisible group. G naught over kappa is a one-dimensional connected p-divisible group. But remember from last time that this is even more classical than it sounds like, because at least I promised you that any such p-divisible group, is a formal p-divisible group and is hence uniquely determined by its identity component from above. And this in turn can be any one-dimensional commutative formal group of finite height. So this is exactly the case studied by Lubin and Tate, except that they didn't make any connection with p-divisible groups. So of height n, and then the infinity ring Lubin-Tate theory is this oriented deformation ring we did discuss last time, or at least a little bit. So it's this orientation ring and then the extension of it, which carries the universal example of an orientation for the universal deformation carried by this ring. In the specific case of K-theory, this was just go to CP infinity and invert the Bott element. And for the ease of exposition, I will also K and localize this, but in the complete account, part of theorem 603 says that this is in fact unnecessary. So this oriented deformation ring in this situation is already K and local, but I don't want to address this just for completeness. I stated here. So this is, well, it's an infinity ring, obviously, and it is complex periodic. Because we made it such, being an oriented deformation ring, and K and local. Well, in this simplified account, this I just K and localized that. So, okay. And now I want to explain that I think we have at least seen all the key ingredients in understanding what the mapping property of this Lubin-Tate spectrum has to be. I hope I can sketch that reasonably. So I give myself just another such thing. Assume A is complex periodic and K and local. So now I want to start this chaos which I announced, but it's a bad point. Time, no blackboards left. So sorry, I have to do some blackboard cleaning. Especially since I have this strong suggestion over there. Maybe one is enough, so it's even more chaotic. So I'd like to sketch why we clearly understand this mapping property of this Lubin-Tate spectrum E. So I want to say something about maps of commutative algebras from E into A. And first off, this is of course the same as maps from the oriented deformation ring into A, because A was supposed to be K and local, and this naturally maps to maps of the unoriented deformation ring. Of course, I'm trying to work towards the only thing we know about the construction is the unoriented deformation ring parameterizes these deformations, and this is what I'm trying to get at. I'm not yet quite here because there's this little difference between ring maps and adic ring maps and so forth. And this is addressed by saying, okay, let's endow the ring A with the IN-A-adic topology, where this is just some scary terminology for the nth Landweber ideal of Quillen's formal group, base change to pi naught A. So once you're over pi naught A, this is really the classical Quillen formal group, and then there's the stratification by height. There are these Araki or generators, P, V1, and so forth, which cut out loci of successively higher height. You look at the nth such thing, where n was the height which we worked on, and of course I'm free to just endow A with this topology. The reason that this is helpful is that I claim all ring maps now are maps of complete adic rings. From the unoriented deformation ring to A, and this is just the naturality of this Landweber ideal. Natural. Any abstract ring homomorphism has to map these Landweber ideals one to the other, so really there are no other ring maps than those of which are adic, and then the completeness is this I assumed anyway. So that these two rings are complete is, maybe that's not so clear now. Okay, this is a relation between K and locality and completeness with respect to the nth Landweber ideal. I think I'm just using this here. But then I run out of space as expected. This is of course exactly what we just co-represented. This mapping space are the deformations, and now I just refill the definition of deformation, so that was a limit over certain finitely generated ideals of definition of Bersotti-Tate groups over A, and sum over pi naught A modulo I, and ring maps. And the question is, what does this arrow refer to? I think this is typically a huge complicated something, and the claim is that one can understand. We're not interested in all these deformations, just in those which are oriented. So I want to understand, or want to claim that one can understand which Bersotti-Tate groups correspond to maps from the oriented thing. That is more or less by definition. I write down the same limit, but there's some interesting things happen. I claim there's just a single Bersotti-Tate group over A which can even occur here, which is this Quillen p-divisible group. And the rest is unchanged, except I just noticed that R naught is kappa, sorry. Okay, and here now something's happening. What can I say here? This is something we discussed, the uniqueness of Quillen's formal group, which is the identity component of some p-divisible group, which is called the Quillen p-divisible group. Okay, what's the reason? So why should that be true? There is just one possible oriented deformation at all, because if you fix the orientation, as we discussed in the last hour, you fix the identity component of the p-divisible group to be the unique oriented formal group, which is this Quillen formal group. So in this deformation, if you insist that it be oriented, there is only one choice for the p-divisible, for the identity component of the p-divisible group, and then there is an additional argument which says that this p-divisible group is formally connected. We've seen one instance of this situation with the equivalence between one-dimensional formal groups and connected p-divisible groups over the field kappa itself, and this generalizes to adic rings and tells that there is a unique such thing. And I realized that maybe this is more detail than I should have given, so I'm a little brief here now. You come to terms with this limit. You can check that rather than taking the limit, you just take one example of I. The nth Landweber ideal is an ideal of definition. It's enough to take that. This uses that kappa is perfect. So if you make little nilpotent changes here, you won't see any difference in the ring maps because you're mapping out of a perfect field. And then, well, you just get maps of formal groups from the identity component of what we are deforming. So this is this Lubin-Tate one-dimensional formal group of height n to, well, the Quillen formal group base change to Poinat A over the nth Landweber ideal. And something, I mean, even if all this went a little out of hand and is too much detail and hard to tell, there is one definite result which is surprising here, which is that this is discrete. Except there is not yet any statement. Okay, there are. Okay. This would be a description of the statement and the proof of theorem 515. This is the mapping property of the Lubin-Tate spectrum. Maps out of the Lubin-Tate spectrum correspond to maps of formal groups, and in particular the mapping space is discrete, which is of course something fairly unexpected for periodic E-infinity rings. And the reason it is because, well, I mean, I omitted some discussion here, which is going to show that you can put a point here, this I discussed, as well as here, because you just fix this ideal of definition to be IN. And then you just look at the loop space of this space of equivalences of p-divisible group, but that's over a discrete ring. And I sort of promised that these spectral p-divisible group over discrete rings work as usual, so they have a discrete space of morphisms. So this is where this discreteness comes from. Now I have to reconsider the rest of the talk a little bit. Well, maybe I can shorten this. Okay. So there is something fairly fantastic coming up next, except that I just decided not to explain it in detail. But there is one, of course, key move I want to absolutely say something about, which is how could you ever try to prove that the homotopy of E is even? The way it's constructed, I mean, there is a little fuss about adic here and identity component there, but it's probably fair to say that this mapping property is absolutely to be expected by the way it's constructed. It's constructed with universal properties and it represents deformations, so it's clear that you know what maps out of this Lubin-Tate spectrum have to be. And of course this typically will not tell you anything about what maps into it. For example, the homotopy groups are, and there are several new ingredients in the proof which I would like to address. Let's see. So, of course, you need a lot of information to, in the end, be able to claim that this is the Lubin-Tate spectrum we know. But let me just, for the ease of exposition, concentrate on trying to understand how one could possibly see that pi star is even. And that involves an interesting way in turning this mapping property we have into some information about the homotopy. So it's through the Adams-Novikov spectral sequence, arguably. So we bring into play complex Bordism. MP is periodic complex Bordism. I think the reason it's not MU that is used in the paper is simply because it's easier to say what MP is as an E-infinity ring than it is what MU is. That's all, and the periodic version is sufficient. So we look at the MP homology of E, and we can use some classical results here which say that this map is faithfully flat. I mean the classical computations of Quillen and Novikov. No, that's wrong. Say, of course, a lot more. I mean, we're just asking what is the E homology if E complex oriented of MP, and of course that's known. And in particular, it says these are free modules, so it's finite flat and everything. And that means it's enough to prove that this is even, to see that E is even. Let's call that A. And there is a little point in between, A twiddle. Let's denote the connective cover by A twiddle, because anyway, let's just do this. But of A, so this receives the map from the connective cover of MP. And one observation here is, of course, that this map inherits a mapping property from the one of E, which we just established. That is sort of extremely plausible. You just base changed E over the sphere to MP, so this algebra will have a mapping property. So I remark that somewhere here, star. If you have any Kn local MP algebra, as for example A, take another one, call it B, then 515, this mapping property which I just discussed, will imply that maps of commutative algebras, say over the connective cover of MP, from A twiddle into the connective cover of B, are given by these maps of formal groups which we've seen before. And actually I want to slightly rewrite this. I want to write this as morphisms of commutative algebras over L over IN from kappa twiddle to B naught. And I think there isn't a single term defined here, unless I'm mistaken. So let's see what's the best order to do this. B naught is simply the reduction of the test algebra you're looking at, so that is immediate to say. B naught is pi naught of B over the nth Landweber ideal. And now we, even without knowing what this says, this one can already see that we're trying to get at a characterization of this algebra A twiddle by a mapping property. And the mapping property, okay, this one is in the world of connective ring spectra, but this looks like all classical rings. So the claim is, again, we have this discreteness and the mapping are identified with some discrete Z, and now I formally introduce all these things, but it's not surprising. So you can truncate to pi naught of MP, which is L, it's the Lazar ring. And you can divide out by the nth Landweber ideal at P. Okay, there's still nothing of our initial data kappa, we started with our one-dimensional formal group G naught naught over kappa, and now we want to say, okay, we know that those are maps of formal groups, and now I'm just trying to mingle in coordinates. We can, it's not necessary to look at formal groups. We can look at coordinates formal groups, because this is what we will naturally see once we work over complex borders, and we will see the Lazaring and formal groups with a coordinate. And there is, of course, one. We started with this formal group over kappa, and there is an extension kappa bar, a kappa twiddle, a kappa bar, which parameterizes coordinates of G naught naught over kappa, and the universal of such will afford a map here. Okay, now I just added a lot of data into this diagram, which is naturally floating around. So let me try to come back, make contact with this B naught. The point being that our test algebra B naturally lives over L over IN. So this is B naught lives here. And now, stepping back a minute and looking at what this is saying, is that maybe I should use color to highlight something. You should think of this as kind of an input datum. So for those who know, I'm trying to explain why this approach of proving that the homotopy is even naturally leads to considering a spectral generalization of the notion of Witt vectors, lifting morphisms mod p to lifting to characteristic 0, because this is naturally the situation we run into. This is all given by the problem here, and then we're trying to understand an algebra A twiddle, which has a mapping property, which says, okay, it's an algebra over something complicated, the maps out of which are the same as the maps out of the reduction down here. So I think, for example, this is the p-adic integers, this is fp, you make a perfect field extension, then you know that the Witt vectors are characterized by the property that mapping out of them is the same as mapping out of the perfect field extension you have here. And this is reverse engineered to say, okay, we'll naturally run across the situation where we want to understand such an algebra, which comes with a Witt vector-like mapping property, and now we go the other way around and check that given this situation, there is a quite canonical and unique way to produce such an algebra, and this proof will actually give enough control to see that this is even, which is still what we're trying to prove. So to make a final piece of connection, maybe there's still some unconnected piece here. The claim is that some obvious map here is a bijection to the map of formal groups. From the formal group we started over kappa G naught naught into the test formal group, which leaves over B naught. Okay. Let's see how bad I can go. So that was a sketch. I'm not sure if it really got across, but I found that idea just too fantastic not to at least try to share a little bit how you would use the mapping property of E to get at its homotopy. What you realize is the mapping property uniquely characterizes it as a Witt vector type of lift of something you can understand and control, and then you reverse engineer and sit down and see in what generality can you produce these Witt vector type liftings, and you will see that this greenly highlighted situation is nicely behaved so that you can always lift this, and then you know that the thing you're interested in is the unique lift of kappa bar over L modulo IN, and that proves in particular that A is even. Let me see.
Where was the last part? Where did we show the evenness? I missed that.
That's not going to come out completely. It's just, the logic is just, okay, I can...
There were a lot of things, and then you suddenly said, no miracle occurs.
Yeah, it's not a miracle, but I mean, it's nice.
Sorry.
So are you saying there's two things with the same universal property and one of them's even, so the other one is? Or?
Yeah, exactly. Let me just try to wrap this up a little better because it did get out of hand. So here's some plus. Plus characterizes a twiddle as the thickening. So that is the technical term which maybe I will address in the remaining 10 minutes as the thickening of L over IN to kappa bar with respect to this sort of reduction map from the connective cover of MP to L over IN, which one can prove as even. And this is where the argument sort of turns around. We know this mapping property, it's characterizing it, so now let's sit down and prove directly in a sort of semi-constructive fashion that such an algebra with this mapping property exists. And in the in the course of this proof, it will turn out that certain properties are inherited by the lift from the thing over which you're lifting, and then of course you know that this is even, and this implies that H twiddle is even as well. But I didn't plan to go into that. But well, let's see what I can do. Well, I can surely just give the formal definition which tries to extract the essence of the situation. This is this thickening which I used anyway. And then I will just probably conclude with a couple of examples. So the definition is as follows. If A is a connective E infinity ring and I in pi naught of A is finitely generated, you can reduce this ring. A naught is pi naught A over I. And you can look at an algebra F naught over A naught, call it B naught, and that is supposed to be discrete commutative algebra. So this is the situation. A would be the connective cover of MP. You reduce it down along some finitely generated ideal to L over IN, and then over this reduction L over IN you contemplate some extension which is kappa twiddle, and you try to lift that back to the original thing. So the definition is a diagram well, I can use more color, I guess. So this was part of the given datum. So, well, a lifting is a lifting. Okay. A diagram of commutative algebras is a thickening of F naught. By definition, if the following three things occur. Firstly, B should be I complete. This is like with the bit vectors. I mean, if you take a finite extension of Fp and you form the bit vectors, of course you get a p-complete ring of bit vectors, and you demand that this be so. Secondly, of course, you want that the thing B is actually lifting what you started with. So that means the obvious ring map from pi naught B to I over pi naught B to B naught is an isomorphism. And then, of course, the most severe demand is this mapping property, which we sort of discovered in nature over here. So for all like rings, like B, so for all connective and I-complete algebras over R, there is a map between mapping spaces of algebras over R into B. Where can I draw that? So here are the test things. Whenever you have triangle here, you can reduce it. Maybe That's the mapping property over A respectively over A naught. So formally this is saying the map of mapping spaces from this map of commutative algebras over A from B into R into the maps of classical commutative algebras over A naught from B naught, is there any B naught? Yes, to pi naught R over I times pi naught R, which is the R naught there. That should be bijective. And in particular, again, you're...
Yeah, and the first one, R and B, need to split.
Oh, I'm sorry, yeah, yes, sure. And now I use that blackboard. Okay, you can just ask this, and then there is a treatment in some generality when those liftings exist and so forth. You need appropriate hypotheses on this map and, of course, on the reduction map. And these all turn out to be fulfilled by the motivating situation I tried to describe over here. So you can then conclude that this A twiddle is the lifting of this F naught here. And in the course of proving the existence of this lifting, you also get some properties, and in particular you learn that the evenness is inherited from the complex Bordism spectrum. Let me maybe just write down one example, which is example 1, which is spherical width vectors. But I'll not touch this here. So you could take A to be the p-adic sphere spectrum and I to be the ideal in its pi naught generated by P. So you would reduce it down to Fp. And then you can take any perfect Fp algebra, and the theorem, which I hadn't time to state, guarantees the existence of a thickening of this thing. And you call this thickening the spectral bit vectors. So this is a connective E-infinity algebra over the p-adic sphere, which is itself p-complete, and which reduces mod p to this perfect Fp algebra. So that is isomorphic to W plus B naught tensored over the sphere with Fp. And it has the mapping property which it has to have. And so that's an example. Maybe if you want an exercise, I'll just give this in words, and maybe I can learn something, and maybe I'm overlooking something. I mean, if you just start with this very down-to-earth lifting problem, you can solve this without any hard deformation theory or whatever. You can just observe that this functor is co-representable because it preserves limits. And the reason it preserves limits is if you change R for a limit here, then you're trying to commute taking the limit over pi naught. That doesn't look terribly good, but the mistake you have in the comparison map is a nilpotent ideal. And by the perfectness of this thing, there is no difference. So it's very easy to prove that there is a unique connective p-complete E-infinity ring with the required mapping property, but I see no way of getting out of this approach the fact that it reduces back to the thing you started with. This is why I think you need a more elaborate approach in proving this to control the properties. In particular, I didn't state the theorem. Okay, so I'm done. Thanks.
Are there questions?
Yes. So the unoriented R is in the case of the multiplicative group, the p-divisible group associated to the multiplicative group, is this unoriented universal ring the thing that's like before you take Snaith's theorem, the sigma infinity of Cp infinity plus?
That's an absolutely fantastic question. Let's ask the audience. Who knows?
Oriented.
Oh, that's the oriented one?
The
Oh,
pre-oriented.
I didn't invert beta yet.
No, sorry. The reason I'm playing on this is because that was the first example yesterday.
Oh, sorry.
So
that
the
wasn't
unoriented
here.
the unoriented thing is the p-complete sphere because there's just the entire deformation theory is trivial. It's the dual of an étale p-divisible group, so there are no deformations.
I see.
And then if
Gotcha.
you
Gotcha.
if you put in the orientations, you do two steps in one. You take the
Oh, I see.
pre-orientations,
One
which is
the
CP infinity,
pre-orientation, one is the
and then
Gotcha.
you invert
Gotcha.
this. Yeah.
Are there any cases where we know this, any other cases where we know this unoriented guy?
I would hope so. We can discuss. I think you can do something like canonical coordinates and lifting ordinary things, but I mean, I think so. I'm not totally sure.
I mean,
He knows.
Jacob said several times that he doesn't know anything about R-un or its homotopy or anything about type 1.
Yeah, sure, you don't know the homotopy, but this is already underlined by the very first example because it's the p-complete sphere. So I think asking,
Yeah, I mean, he doesn't. He just said he didn't know anything about it.
no,
What is it for a finite when we start with a finite field? Fp? Some finite field of characteristic p? Fp to the n, what do we get?
what group do you want to take?
Again?
What group do you also have to give me a group you want to deform, not just the ring to start with.
Multiplicative again?
Yeah, this leads, of course. I mean, then you just base change the thing you deform, so you look at a subcategory of deformations, and this will give this lift, I
With
guess.
this we're joining roots of unity prime to p, which we know we can do.
You can do.
So that's what's happening. I see.
How close are you to calculating pi 0? This is one thing left, right?
Exactly. Yeah. This I didn't say anything. I mean, it's this. No, for this you have to go. I mean, no, you have to go deeper, and you divide out the familiar regular sequence p, v1, and so forth, and you control the smallest quotient and prove that it is what it has to be, kappa twiddle roughly, and then you work back because regular sequences and so forth. I skipped over this.
So you described a complex periodic E-infinity ring spectrum that you get this quill-informal group. And so is there a way I can get a p-divisible group which is not constant if I start with something which is equivariant, like a global E-infinity thing, and take the c p to the n fixed point under some circumstances?
Sorry, memory full. Can I'm happy to discuss this afterwards. It's okay. I don't know.
There's a comment that says something like that in the paper.
There is a comment which says this in the paper. What's the? I don't know.
He asked if you can. So when you have a complex periodic ring, you get a formal group over this ring, the equivalent group. And he's asking if you have an equivariance theory, then can you get an actual p-divisible group, something finer. And okay, yeah, there's a comment saying that in a future paper or something like that.
This is videotaped, isn't it?
Are there other questions? Let's thank Niko again.